Let's talk about the plus sign, the minus sign, the square root symbol. We use them every single day, right? We never even think about them. But here's the thing, these tools weren't just found lying around. They had to be invented. And the story of how they came to be, well, it comes from one incredible book. A book that was literally pieced together from the scattered notes of a genius long after he was gone.
No, seriously, think about that for a second. How would you even write 2 plus 2 if you didn't have the plus sign? Or figure out the square root of 9 without that little checkmark symbol? For most of human history, math was just this messy tangle of words and weird, competing notations. It was a problem just begging for a solution, and the guy who finally solved it was John Napier.
All right, so let's dig in. Our guide on this journey isn't actually a person, it's a book. And this book has an origin story that's every bit as fascinating as the ideas inside it.
So this book, the source of all this innovation, is called Arte Logistica. But it wasn't some polished, finished product. In fact, while it was Napier's most detailed, most ambitious work, he actually died before he could finish it. The version we have today was literally pieced together from his incomplete notes and fragments, and it was published years later by one of his descendants. We're essentially looking at a master's unfinished symphony.
Okay, so we've got this unfinished book that was cobbled together from scraps of paper. But why was he writing it in the first place? What was Napier trying to do with all these scattered notes? And that brings us to his big idea, his mission to define the very art of computing.
Yeah, what was the grand plan here? Why spend years designing a whole new system of symbols and rules? Was he just doing math for the fun of it? Or was there a bigger, more ambitious goal driving him?
Well, the answer is hiding in a single, really elegant Latin phrase that he jotted down in his notes. This was basically his mission statement, his whole reason for doing this. Logistica is ars bene computandi.
Logistica. It simply means the art of computing well. And that one phrase, it reveals everything. See, for Napier, math wasn't just a bunch of abstract ideas. He saw it as a practical system, an art form even, with one single goal: to make computation effective, efficient, and consistent for everybody. And to pull off that vision of computing well, he knew he couldn't just tinker with the old methods. No, he had to go right back to the very beginning and build a brand new logical system from the ground up.
He started with the absolute basics, defining and standardizing the 4 operations that are the bedrock of arithmetic: addition, subtraction, multiplication, and, get this, what he called partitio, which is just a fancy Latin word for division. By giving them formal names and rules, he was creating a universal language.
But just defining the operations isn't enough, right? You have to be able to write them down. And this is where Napier drops one of his most famous, most lasting contributions. He formally introduced and popularized using the plus and minus signs, just like we do today. I mean, it seems so simple now, but it literally changed everything.
And what's really fascinating here is that Napier was kind of playing 2 different roles at once. When it came to algebra, he was cool with just adopting the symbols that other people were already using. But for arithmetic, the art of computing, he saw that what they had just wasn't good enough. So he decided to invent something entirely new himself.
Oh, and his creativity didn't stop with plus and minus. Not by a long shot. To deal with the tricky problem of roots, square roots, cube roots, and all that, he came up with this really clever visual solution that starts with this simple grid of numbers. It looks super basic, I know, but this little grid is the key to one of his most brilliant ideas. He then says that the very lines making up these boxes, in his words, the boundaries of the cells, are radical signs. And a radical sign is just the official math term for a root symbol, like the one we use for a square root.
And this is just so cool. Look at the box around the number 4. If you just take the top line and the right side line of that box, what do you get? Bam! The modern square root symbol. It's this elegant visual way to show a complex idea, and it comes directly from this simple grid.
Okay, so Napier has this great system for operations and roots. But his system also had to deal with the most mysterious, most difficult numbers of all, the irrationals.
Back in his day, these numbers had an awesome name: surds. These are the roots that don't give you a nice, clean, whole number, or a simple fraction, like the square root of 2. The ones that go on forever without repeating. They were a massive headache for mathematicians.
And you gotta respect Napier, because he was totally honest about the challenge here. He wrote that when you're dealing with surds, this number cannot always be found. Even the guy who was architecting this whole grand system had to admit that some parts of the mathematical universe were still fundamentally mysterious.
The final piece of his system was to create a clear language for positive and negative numbers. And his first attempt at naming them is just fantastic. Instead of positive and negative, he used the words abundantes for abundant quantities and defectibus for defective ones. It's just this amazing little window into how people were first trying to wrap their heads around these ideas.
So when you put all of these different pieces together, the signs, the operations, the notation for roots, the way he tackled these weird numbers, you start to see the true scale of what he accomplished.
I mean, when you lay it all out, you see it wasn't just one thing. He built a complete computational system. He set down rules for all kinds of numbers, integers, fractions, even those tricky surds. He formalized the plus and minus signs we all use. He standardized the 4 basic operations, and he created that brilliant visual system for finding roots.
He didn't just solve a few little problems here and there. He built the foundational language of modern computation. It's like an invisible operating system that powers so much of our science, our engineering, our technology. Every time you pick up a calculator or write a line of code, you are speaking Napier's language.
And that really leaves us with a final thought, doesn't it? Napier's system is all around us, totally hidden in plain sight. It just makes you wonder, what other invisible systems, things that were designed centuries ago, are quietly running in the background, shaping the way we live and think every single day?